So here's the final product in action. Is the view worth the climb? Yeah, I think so. We're going to see how to build a 3-track traverser table. A traverser table is a flat table that moves back and forth to align with stationary tracks on either end. It allows you to shuffle cars between the tracks without having any ladder tracks. I use it to stage trains for entry onto the layout and to receive trains coming off the layout. Keep in mind that this is just my way of building the thing. Other folks have been successful using other techniques. Be sure to look in the comments section for links to things like build plans, Sketchup models, programming code, parts lists, etc. What do you get for your efforts? A 3-track traverser table. There is one exit point to the right. A motorized table movement. We use a cool stepper motor for that. A touchscreen panel. We get a control panel with graphical buttons that work like an iPhone. Reliable operation. The control system hits the track stops every time. Ability to fine-tune the alignments. You can dial in the alignments darn close. Before we get too far, let's talk about money. This is not a cheap project, but it's not $1 zillion either. It will likely cost you a few $100s plus your time. You'll need wood, bolts, screws, wire, USB cables, and some aluminum L-angle that's all easy to find and kinda cheap. We'll cover the special parts you'll need as we go along. I built the control system first. Ignoring the pole, it looks pretty sweet. The user interface has 3 panels. While on one panel, you switch to another by touching a tab at the top of the panel. The Basics panel shows you where the table is with relation to the transition track. Push a button to align the transition track to one of the 3 tracks. The Adjustments panel lets you nudge the table up or down to line up one of the tracks with the transition track. Then you can set a track stop. Use the Settings panel to save your stop information for reuse later. We use free software to program the device, but we won't show any of that today. I'm sure you'll be happy to hear that. All of the components for the control circuit are wired onto a single PCB board to which all the inputs were connected. The control system is driven by a custom program that is stored on an Arduino microcomputer, but we won't show any of that today either. If you build and test the control system first, you can run tests when building the physical table. Here's the special parts you'll need for the control system. On Arduino Mega, you'll store your control program on this microcomputer. A PCB board. I use this version, but others exist. A power supply. This one is likely oversized, so choose your own. The Nexion touchscreen unit. Get this version because it comes with a nice enclosure that easily mounts in a rectangular space cut into wood. Stepper motor and driver. Get these specific doodads because 1, they work great, and 2, my control program is coded to drive these specific devices. An optical sensor. This is used to find the home position. Amazon has many models. Here's a model illustrating the travel distance of the traverser. The tabletop has a home stop a bit to the left of the stop for track 1. This is the leftmost limit of movement as viewed from this end. The rightmost limit of movement is the stop for track 3. The distance between these two is defined as the travel distance, and mine is 5.5 inches. I added a cushion of 3/4 inch to get what I call the working travel distance of 6.25. We need this number to decide which linear actuator kit to buy. Here's the traverser with the tabletop and the transition track removed. That centerpiece is called a linear actuator, and it causes the table to move back and forth. A vendor sells complete kits to make these. The Linear Actuator Kit is sold by OpenBuilds, and it's called their V-Slot NEMA 17 Linear Actuator Bundle Lead Screw. The vendor offers models with these lengths, and each has the travel distance shown here. The 250mm version looks like it might work for me. You should order and build your kit before you do any more design work, so you have some important dimensions for subsequent design work. Here's the most important parts of the kit. Thankfully, the vendor has a video showing how to assemble it. There's a link to it in the comments. But we aren't building a 3D printer, are we? No. So you do not want to just blindly follow their instructions. You need some more information to pull this off. First, I think I found a mistake in the kit. The stepper motor is supposed to attach to the front end plate with 3 supplied screws. However, as you see in this photo, the screws are too short, and the long spacers are also a bit short. To fix this, I got some longer screws and used them and some jiggered up spacers to get the stepper motor properly mounted. It's no big deal, it's just something you need to fix. The kit ships with some number 10 self-tapping screws, which the video says to use to attach the end plates to the V-Slot rail. Throw them away. Don't use them. Throw them away. We need the holes in the end of the rails to be tapped with machine threads down about 1 inch. Again, do not use the included self-tapping screws. Tap the holes down 1 inch with a 1024 tap and then use number 10 machine screws. Use number 10 machine screws of about 3/4 inch length to temporarily attach the end plates to the rails. We'll replace them later with longer screws and some nuts. At the end, the video shows that the lead screw ends nicely at the back of the unit. Well, my lead screw didn't. It extended out the back a little bit. I don't know, I don't care at this point. Enough of the scary stuff. Just watch the vendor's video with a few extra screws and spacers and you'll be fine. After you're all done, remove the gantry plate from the unit and attach 2 pieces of wood according to the build plans. These photos show you what mine looked like. You need to ensure that your actuator delivers the amount of travel distance that you need. I'm using a model to show you how to do this because I didn't take photos of my own efforts. Don't rely on a model. For sure, don't rely on mine. Do the process that we're going to talk about and do it in real life with a real tape measure. Place the actuator upside down on a board so that the unit runs parallel to one edge and is flush to that edge. Clamp the gantry to the board. Position the gantry so its back edge is 1/2 inch from the outside edge of the back support plate. You can do this by firmly pushing the gantry plate and letting the lead screw turn, or alternatively, you can turn the lead screw by hand. Mark on the board where the outer edge of the back support plate is. Move the whole unit by turning the lead screw so that the front edge of the gantry plate is just a shade away from the last place it can stop. Again, mark on the board where the outer edge of the back support plate is. Measure the distance between the 2 marks on the board. It needs to be greater than or equal to your working travel distance. I was shooting for 6 1/4 and I fell well short. I ran this test in real life and got pretty much the same answer. Not enough travel distance because at the front of the actuator, the edge of the gantry plate was hitting the front bearing too soon. The fix was to add enough washers under the gantry plate to raise it so it would clear the bearing. On the model, I just raised it magically via software. Now I was able to move the gantry a little closer to the front of the actuator and I barely got the needed travel distance. In real life, my travel distance was close to 6 inches and I was okay with that. To figure out the best width of the frame, we first look at the assembled actuator. Measure from the outer edge of the back plate to the outer edge of the front plate as shown in the diagram. Draw a line of that length on a big piece of paper or board. Now, on the right side, add 3/4 inches because that's how thick the frame is going to be. This represents where the back frame will be. To attach the front of the actuator to the frame, we use 3.5 inch long screws. The screw is screwed into the rail about 1/2 to 3/4 inch, and then a nut is tightened against the front plate. Measure from the outer edge of the front plate to the inner edge of the long screw. Add this measurement to the left side of your drawing. Draw another line 3/4 inch in from the leftmost end to represent the width of the front frame. This drawing shows you how to interpret your diagram. The number we really care about is the width of the frame from outside edge to outside edge. The model shows this is 13 and 27/32 of an inch. In real life, mine came out to about 13.5 inches. You can fudge maybe a little, but be careful. My real-world efforts showed that my frame can be 13.5 inches wide outside to outside and 12 inches inside to inside. So from now on, that's what we'll use. As long as you have the frame width from the last effort, you can draw the beginnings of your frame. Do that. Just make sure the width is correct. Nothing else really matters. We want a slice of the table as seen from the right end. Draw a narrow rectangle under the frame extending past the front and the back sides. On that rectangle, mark where the front and the back sides of the frame lay on the rectangle. Remove the frame, and we have a narrow slice with two brown parts that show where the front and back pieces of the frame are located. We've added in the important measurements for my table. Because we moved the gantry plate 1/2 inch from the back frame earlier, draw a line 1/2 inch from the back frame now to mark that starting position. Because the gantry plate is 3.5 inches wide, draw a line 3.5 inches out from that spot. We know the travel distance, the real travel distance, is 5.5 inches, so we mark that also. The red area marks the combined length of the gantry plate width and the travel distance. Plus, and this is really helpful, it shows us where the table will be positioned relative to the frame when the tabletop is at the home position. The green area in front of track 1 is where the home stop will be. It should be enough to provide some safety space next to the home stop. 1 inch is enough. The blue area should be at least as big as the green area for weight balance. I added an extra 3/4 inch because I thought it would be smart to add a little extra weight near the back, but not too much. These are all judgment calls. The tabletop width comes out to 11 3/4 inches. This is an excellent time to calculate where the bearing plates will be attached to the tabletop when it's in the home position. The bearing block is about 2 1/4 inches wide. The bearing plate is 4 1/4 inches wide. I decided to center the plate across the tabletop width. Doing the math, I got about 3 5/8 on one end and 3 7/8 on the other. After verifying that the bearing block wouldn't hit anything during the table's travel, I was happy. The diagram shows the bearing plate in the home position. To help position the bearing plate during its installation, I noticed that the distance from the inside of the front frame to the front edge of the bearing block is 6 1/8 inches. That's a magic number we're going to use later. We need to be sure that we can fit the traverse between the aisle and the back wall. The location of the exit track is the key constraint because our transition track must line up with that. The distance from the center line of the exit track to the room wall was measured in real life at 13 1/4 inches. On the diagram, I just drew a big fat line of that length. The left end of the travel distance is the home stop. The center line of the transition track is 1/2 inch to the right of that. So we mark on the right side of the board where the center line of the transition track is. We move our measuring stick to line up with the marked center line. Remember that the transition and the exit track share the same center line by definition. So we are also measuring the exit track center line. Extend the right edge of our board to match up with the end of the measuring stick. We see that the distance from that right edge to the room is 3.5 inches. As long as it's well over 0, we're golden. Draw your plans as detailed as you can. These are overview drawings of the unit we'll be building in the rest of the video. I use Sketchup to draw them. Use whatever you want. Buy the special parts you'll need for the frame in a kit from Ziltech. We show the available links here. The stated length refers to the exact length of the rod. The minimum size you need is the width of your frame, outside to outside, plus 2 times the width of the chrome support blocks, which is about 5/8 inches. According to the model, I need a minimum of 14 and 19/32 of an inch, which is about 370 millimeters. So I got the 400 millimeter kit. This image shows what one of the 4 supports look like after it has been attached to the frame. Here's the dimensions for the support. In hindsight, I would probably make them around 2 inches by 6 inches just to give a little more room for attaching it to the frame. After cutting the support to size, I marked the center line on top. I clamped it to another piece of wood that was around 4.5 inches high and replaced the support on the block and drew its outline. I used a centering punch to find the center of one of the pre-drilled holes in the support. The dimple helped me drill the hole with a drill press. Screw in one side and then you're set to drill and screw the other side. Repeat this on the other 3 supports. To get the 2 pieces the exact same size, I first clamped them together and then I screwed them together. I clamped and cut the 2 pieces at one time on the miter saw. Hey, don't even think about unscrewing them yet, because there's more fun to come. Write on your 2 joined pieces stuff that tells you which piece is the front versus the back and which direction is up and down and right and left. Believe me, you're going to forget this stuff. This shows you where the center line of the 2 bearing blocks needs to be. Mark the center lines on the top edge, the front and back of your just cut pieces. I took special effort to ensure that the support blocks were flush with the top of the long pieces. This is critical to ensure that the rods sit level. Work with the front of the 2 pieces facing up towards you. Clamp a back piece of wood to the top of the 2 long pieces. Position the support block so that it's centered over the marked center line. Clamp the support block onto the 2 long pieces with the top of the support flush with the backer piece. Drill holes and screw the support block to the face of the wood. Leave the backer piece in place and repeat this process for the other end. Use a drill press for this step. Can you use a handheld drill? Nope. I'm embarrassed to say that initially my drill press table was not perfectly perpendicular to the shaft of the drill press. So to avoid some rework, check your drill press alignment now. Position an 8mm drill bit into the hole in the metal support piece and drill into the 2 pieces of wood with one movement. They call this match drilling. Insert one of the chrome rods into both holes you just drilled. Visually and with the aid of a level, check that they are perpendicular to the frames. Hey, don't take those 2 pieces apart yet. We're not done. We need to match drill 2 3/16 holes, and the diagram gives us enough dimensions to get things in the ballpark. What matters is that the 2 holes are the exact correct distance apart and they are as level as possible. The good thing is we'll use the end plate as a template later to get the 2 holes the right distance apart. From the left end of the front piece, mark off a line at 22 3/4 inches, and it doesn't need to be exact. Somewhere there is close. Cut a spacer plank of wood that's about 24 inches long, 3/4 inch thick, and close to 1 13/16 inches high. Mine was the length of the whole front piece, but you don't need that long. Just make sure that the piece is the exact same height, around 1 13/16, or close to it, from end to end. Clamp the spacer plank along the bottom edge of the front piece. Remove one of the end plates from the actuator. Position it as shown. To get the correct alignment, do this. Get a 3/16 drill bit with a brad point to use as a center punch. Place the end plate along the top edge of the spacer plank and make sure it is always touching. Slide the end plate until the plate is roughly centered over the vertical line you just drew. Put the drill bit in the rightmost slot and make sure it's touching the top of the slot. Tap the bit to make a nice indent. Remove everything from the wood and use a 3/16 bit in your drill press to match drill a hole through the 2 pieces at one time. Now remount the spacer plank as before. Insert a number 10 screw through the right slot of the end plate and then into the hole you just drilled. The end plate should be flush against the top of the spacer plank. Secure the screw with a nut. Place your 3/16 drill bit, that one with a brad point, in the left slot this time, and make sure it keeps touching the top of the slot. And also make sure the end plate is flush against the spacer plank. Tap the drill to make an indent and match drill the hole as before. Now you can unscrew those two long pieces of wood from each other. On the back frame, reattach the end plate where it just was. Slide it down until the screws are touching the top of the slots. Using the end plate as a template, drill a hole as big as the big hole in the template as shown here. This gets you started making that goofy shaped hole in the back frame. To attach each of the other two bearing block supports, use a chrome rod to hold a support in place, along with clamps, as you drill and screw the support to the face of the frame. It would be best if you also clamped a piece of wood to the top of the frame to keep the block flush with the top. Here's a diagram that shows the shape and size of the goofy hole in the front frame. While SketchUp can produce dimensions down to a gnat's eyelash, we don't need that kind of precision, but you do need to be as good as you can get. We just need a hole that the stepper motor can slide through without hitting anything. As you'll see, my final hole looks pretty ugly, but I got the clearance I needed. Here's what is important. You see that 11/64 of an inch worth of wood between the screw holes and the slanted edge of the hole? Watch that. Keep that small piece of wood from getting too thin. I suggest you make a template on a smaller piece of wood and use that to mark an outline on the real frame. Using the template, I marked the outline and then drilled big holes just inside the markings to remove lots of wood. You can use a scroll saw or a saber saw to cut off the remaining largest chunks. Then use a rasp and a file to clean it up. Again, be careful as you cut near those two mounting holes. I've drawn the back hole as a square hole, but you can cut it as I did with round edges. Use the same template technique as before. We'll build 3 cross pieces and 2 smaller spacer pieces, all out of 1x6 poplar. The dimensions are shown in these diagrams, and the top view shows you how each piece is positioned and some basic dimensions. The left end will be attached to one of the vertical supports. It is slotted to allow for movement back and forth. The middle cross piece is close to the right end. It will be attached to the other vertical support and is also slotted for the same reason. The right end is just a plain piece of wood with no slots. Yes, you'll need to build those 2 spacer pieces also. No big deal. Since building these pieces is nothing special, we won't spend any more time on them. Here's what we're after. Actually, 2 of them. We'll attach 2 pieces of wood to the top of the bearing block to get the height we need and to allow us to attach the plate to the underside of the tabletop. Pretty basic, really. Cut out the 2 rectangular pieces according to the plans, or close enough. Get some appropriately sized metric screws that will reach down through everything. Drill the holes in the right spot, countersink the holes in the top of the top piece of wood. Here's what a bearing plate looks like on top. Full disclosure, this was my first attempt and it was not high enough. It turns out that light brown part was actually sitting low enough that it hit the frame when I moved the table. Bad news bears. My solution was to use 4 nuts as spacers to raise the top piece of the plate. A better solution is to use 3/8 inch plywood, so that's what's in the build plans. I didn't want to replace the pieces I already cut, so I raised each one of them with some properly spaced nuts repurposed as simple spacers. It worked out okay. Pretty easy, really. Slide a chrome rod through one of the bearing support blocks at one end, and once you're in, slide on one of the bearing plate thingies we just made. Then you want to push the rod through it until the rod reaches the opposite frame. Push it through the hole, through the bearing block support on the front frame or wherever, until the rod is flush with the front of the support block. Then tighten the set screw. Do the same thing for the other plate. Yeah, that one was easy. This one ain't. Because the actuator cannot be wrangled into place if it's left fully assembled, we remove the stepper motor and its associated little parts. Place the actuator between the front and the back pieces of the frame. Attach the actuator to the back frame. Here it is approaching the back frame with its mounting screws and end plate still in place. Remove the mounting screws, end plate, and other small parts. We don't want to release the locking collar, however, from the lead screw. Push the mounting screws through the 2 holes and then slide on the end plate, bearing, and washer. Slide the actuator up to the 2 mounting screws. Prop up the front end of the actuator to keep it level. Jiggle everything into place and screw the mounting screws into the rail, but don't fully tighten yet. This is what it looks like in the front after you're done attaching the actuator in the back. The stepper motor is initially outside the frame along with the 2 mounting screws and nuts. A lot happened since the last photo. Because the end plate won't fit through the opening in the wood, you need to detach the end plate from the stepper motor, put the end plate inside the frame, and then reattach it to the stepper motor. Given the tight quarters, this takes at least 1 beer. We have pushed the 2 mounting screws through the frame and threaded a nut onto each screw. Push the mounting screws through the slots in the end plate. Push on the stepper motor until you can jiggle the lead screw into the coupler, as well as line up the 2 mounting screws with the holes in the ends of the rail. Try to get the unit as level as possible in both directions. Then screw in the front screws until they're fairly tight. Tighten up the back screws, and then finally, when all feels good, tighten the nuts up on the front end plate. The tops of the 2 bearing plates and the wooden gantry platform need to be even with each other to ensure smooth operation. Here's a level along the frame. It's at 0 degrees. Here I placed a piece of aluminum angle across the 2 plates, the 2 bearing plates that is. The same calibrated level placed on that aluminum reads 0.1 degree. That's good enough for me. But what if it isn't? Well, you could add shims under one of the bearing plates to compensate. Now, we need to get the gantry plate even with the 2 bearing plates. Put the aluminum angle across all 3 plates. Cut a piece of wood that will be screwed to the top of the other 2 pieces. On that 3rd piece of wood, try to get at least one side of the gantry plate pretty close to the level of the bearing plates, but still positioned a bit below the level of the bearing plates. Count on one side being a little better than the other. Now, use shims of metal and paper to get the entire gantry top even with the bearing plates from end to end. Mine ain't pretty, but it got the job done. Eventually, I'll use clamps and positioning jigs to keep the tabletop in the correct position while we attach it to the gantry and bearing plates. This shows the key dimensions of the jig that's used in the lower right corner. To aid in using the jig later, make sure that the depth dimension, in my case 2¼ inches, is the same distance that the bottom edge of your table will be from the front edge of the front frame. This diagram shows the piece at 1 inch thick. Adjust yours to whatever works for you. The top edge of the piece should be close to the middle of the bottom plywood. Screw it into the top of the frame so you can align the next pieces. Cut the aluminum angle pieces and position them as shown. The exact lengths aren't really that important. Just make sure the faces of the aluminum angle pieces are correctly positioned. Cut the other jig to the same size as the first one. Position it near the left end of the frame with the bottom edge flush with the face frame. Cut a piece of aluminum angle and screw it in like you did before. Ready for duty. Screw them in now because you'll need them in the next phase. Cut your 3 pieces to the size as indicated. For the top I used 1/4 inch Luan plywood, which isn't really a 1/4 inch, but you know. The middle is made of 1/2 inch closed cell neoprene sponge foam rubber. You can get it on Amazon. I recommend that you actually use 3/4 inch instead. The bottom is 1/2 inch plywood. For the bottom, please get the best plywood you can afford, and do not, I repeat, Do not use MDF or particle board. Place the Luan plywood on the table so it's flush with the right edge of your positioning jig. Gently move it up, trying to keep it from moving left or right until you see the two bearing plates and the gantry platform. Use a square to mark vertical lines to tell you where the bearing plates and the gantry plate will be. Draw your lines and mark up the areas clearly as no drill. Because I had built a previous table, I had a Luan template with the necessary slots already routed out. I laid that template on the Luan plywood to mark out the slots for the right side. Each slot is 1/4 inch wide and 1 inch long. Check the build plans for more details. Mark out where your slots should be. Make sure you don't mark any slot cutouts in the no drill areas. Route out the slots. On the left end, you route the slots all the way through the end of the plywood. We'll join the 3 layers in the order shown here. Secure the foam to the 1/2 inch plywood with tape. It's best to position the foam just shy of the right edge of the bottom plywood, although this might be a little overkill. You just want to avoid the foam rubbing anything as the table moves back and forth. Carefully align the Luan plywood on top with its edges matching those of the other 2 layers. Clamp everything down. Drill 1/4 inch holes through the foam and the 1/2 inch plywood using the slots as your guide. To ensure that the adjustment slots can do their job, drill your holes just a bit to the right of the center of the slot. From the bottom, insert a 1/4 inch bolt of the proper length up through the 3 layers and secure it with a nut. And here's the tabletop, ready to go. We get the actuator into the home position, which is with the back edge of the gantry plate 1/2 inch from the inside of the back frame. Flip the frame upside down. Make sure your actuator is still 1/2 inch from the inside of the back frame. Slide the tabletop under the frame and move it so that the edges line up with your positioning jigs. Use some long clamps to hold the tabletop firmly against the positioning jigs. Before you commit, verify that the tabletop is firmly against the positioning jigs. Verify that the back edge of the gantry plate is 1/2 inch from the inside edge of the back frame. Verify that the tabletop is touching both bearing plates and the gantry plate by sliding something between the tabletop and the plates. If you get a different level of resistance, check your overall level. Don't get in a hurry. Make sure everything is as perfect as possible before moving on. I used a pre-cut measuring stick to position each bearing plate and then screwed it to the tabletop. I then screwed the top part of the wooden gantry platform to the tabletop. Physically push the table back and forth to make sure that nothing gets in the way of anything else as it goes all the way from the front to the back. No detailed plans for this because there's about a zillion detectors you could use. We use the same 3/4 inch stock that we've used for everything else. I built a good sized base for the detector to sit on, and note that I had to file out some small slots so that the PCB board would sit flat. Hook up your control system so that the detector will light up when triggered. Move the table to the back. Clamp a piece of aluminum angle as shown. Put the detector on the outside of the frame and position it so that it lights up. Give a little wiggle room vertically. Mark where the bottom of the detector is on the face of the frame. Remove the detector and the aluminum angle, push the table out of the way, clamp the detector back where it was, and drill some holes through the detector base and into the frame. Remove the detector and complete drilling the holes through the frame. Put the detector on the inside and screw it in. Put the table in the home position using your positioning jigs. The detector is firmly in place and the tabletop is at the home position. Cut a piece of aluminum angle like this. I use the same 1x1 aluminum angle I've used everywhere. Note that it has adjustment slots. It should be about 3 inches long. Put the angle piece in place so that it lines up with the gap in the detector and is just shy of making it light up. Put in your screws so that the adjustment slots will allow you to slide the piece up and down enough to hit the gap. Get the screws just shy of tight. Move the piece up and down to light up the detector. Then tighten up the screws. Drill a hole to feed the wires through and fix up some sort of strain relief. That was quick, huh? This is just standard track laying stuff. I should point out, however, that on the right end, closest to the transition track, I made sure that the road bed was just a hair shy of the end of the plywood, because as the table moves back and forth, I didn't want the homosode to have any chance of obstructing the table movement. Here's the working dimensions for the entire unit. You have the big wood part, the aluminum angle, and the top homosode row bed, plus of course the track that we don't show. I guarantee your thickness will not be 1 51/64 of an inch. You will see that you're trying to get close, but not quite up to the level of the tabletop. The thickness of the wood piece at the right, where it's thinner than the rest, is very important, and more on that later. Glue up a block of wood using as many layers of high-grade plywood as you need to make sure the block is taller, wider, and longer than you need. The top glue-on sheet will probably not be even with the right edge of the foam and the bottom plywood. Loosen all of the nuts on the top of the Luan plywood so you can move the Luan plywood back and forth. Slide the Luan plywood so that it's exactly even with the bottom layer of plywood. The foam in the bottom plywood should not be moving. Now tighten all the nuts just enough to secure the top plywood from moving. The tabletop height is now at its highest possible elevation. We do not want to match the transition track to this elevation because that gives us no room for adjustment. I got a scrap piece of wood that was a bit narrow and ran it through the saw with small cuts until it was the same height as the tabletop is now. To determine the desired thickness of the piece of the transition track that touches the exit track, go to your exit track and measure as precisely as you can the thickness of the plywood at the end of the exit track. Let's say it was 0.2137 inches. The thickness of the thin side of the transition track should be just a hair thicker than that because, at least on my layout, I can easily shim the exit track up to the level of the transition track, but it's really not practical to shim the transition track up to the level of the exit track. So I use my best table saw skills to cut a series of grooves to make that rabbited end look like this, and the thickness of that top thin part should be very close to 0.25 inches. Cut off one end to get the part to the correct width. Now, remember that narrow piece we cut to the exact height of the tabletop? Use that to set your saw fence. Then move your fence a little bit closer. Make test runs with scrap pieces until your scrap piece, when placed on the frame, comes up to the level you are happy with. After you're dialed in, run your real piece through. Then, cut off the end opposite the rabbited end to get the correct length. This is a good height for the transition track. Cut a piece of 1x1 aluminum angle and screw it into the end of the transition track. This was an early attempt. The final piece was actually a little bit longer. Of course, I also laid track and attached feeder wires. I took the transition track to the exit track and clamped it into position. I match drilled a hole through the wooden border of the exit track and the aluminum angle beneath it. Then I inserted a screw and a nut and tightened it pretty good. I clamped the piece again and drilled the same type of hole in the right border of the exit track. Hook up your control system and have the table find the home position. Position the transition track so that its front edge is even with the front edge of the tabletop. This should put the center line of the transition track about a ½ inch away from the track 1 stop. I know this diagram doesn't show the tracks. Big deal. Do a pre-position and mark and drill holes in just the borders of the transition track, but not the frame. Just make sure the transition track center line is pretty close to a ½ inch away from track 1 stop. The most important distance is how far is the left edge of the wooden block of the transition track from the right edge of the tabletop. I can't give you a measurement, but it should be as close as you feel comfortable with that ensures that there is absolutely positively no contact between the tabletop and the transition track as it moves back and forth completely. I made my best guess and clamped the transition track in place and then manually moved the table along its entire width. Once all was good, I drilled holes in the frame and secured the transition track to the frame. Before laying the track for track 1, use your control system to move the table so that the center line of track 1 lines up with the center line of the transition track. The photo shows that the end of the track spans the gap of the table and the transition track. It gets close but does not touch the transition track. I used the nuts on top of the Luan plywood to move the top laterally just a smidge when laying the track for track 1 so that I got things right where I wanted them. Then I snugged them up to lock that lateral movement. I used flex track. Now the shortest length of the tabletop allowed the rails of the flex track to actually move a bit if there was any jostling. To address this potential problem, I used track spikes to secure the ties, and I alternated the sides on which I installed the spikes to make sure the webbing was not going to move laterally. I then made sure the rail was exactly where I wanted it. Finally, I used CA to permanently bond the rail to the ties in just a couple of places. Once I had the track installed for track 1, I used the nuts on the right end to push the plywood down to get nice vertical alignment. It was during this effort that I kind of wish I had used 3/4 inch foam instead of 1/2 inch. I then used the control system to move the table to get track 2 aligned with the center line of the transition track and redid the same process, and the same thing with track 3. I attached track feeders to all the rails and attached them to barrier strips so that I can connect to track power easily later. I also installed similar barrier strips at the transition track end of the table. This shows you where the end supports are located with relationship to the frame. Both of them have the same dimensions, so build 2 of them at one time to save yourself some time. All the bolts are 1/4-20 and all the routed slots are 1/4 inch. All the aluminum angle is 1x1. Here's the dimensions of the parts of the supports. There's nothing special about the build process for these parts, so we'll just move on. Consult your own plans to determine where the bottom bearing plywood should be positioned. I added some horizontal pieces to the supports to make it easier to secure the bottom bearing plywood. I made sure that the front edge of the supports were positioned at exactly where the front edge of the bottom bearing plywood should be. Wrangle the plywood over the 2 supports, line up the front edge, move it laterally until it's good enough, and screw it into place. This should be good grade plywood that can hold the weight of your table. I used 1/2 inch and it's fine. I put the traverser unit on a table so the ends could hang over. I bolted the end supports so that the table was level and would almost reach the final elevation. This takes 2 people. Move the unit so that it's sitting on the bottom bearing plywood. Move the unit up and over until the transition track mates up with the exit track. Yes, this does take some finagling, clamping, screwing of bolts, etc. The goal is to have the transition track mated up with the exit track with the screws, and to have the overall table as square as possible, and with the aluminum angle at the bottom sitting perfectly flat on the bottom bearing plywood. Not easy, but doable. Make sure the transition and exit tracks are mated well, that there is virtually no gap between the transition and exit track, and that the screws that attach the aluminum angle to the exit track are tight. Go under the table and drill holes in the bottom bearing plywood to match up with the holes in the horizontal legs of the aluminum angle that's sitting on the plywood. Then bolt everything down. Hook up all your pieces and parts of your control system. Hook up your track power. Fire up your layout. Give it a go. It'll work. Hey, I know it was a long slog. You're a real trooper for sticking around to the end, you know. I hope you found a few nuggets here that might help you if you're interested in building this type of project for your layout. Thanks a lot for watching.